Over the years, it became clear that DES and triple DES are simply not designed for modern hardware and are too slow. As a result, NIST started a new process to standardize on a new block cipher called the Advanced Encryption Standard, or AES for short. NIST started this effort in 1997 when it requested proposals for a new block cipher. It received 15 submissions a year later, and finally in the year 2000 it adopted the cipher called Rindel as the Advanced Encryption Standard. This was a cipher designed in Belgium, and we already said that its block size is 128 bits, and it's got three possible key sizes: 128 bits, 192, and 256. And now the assumption is that the larger the key sizes, the more secure the block cipher is as a pseudo-random permutation. But because it also has more rounds involved in its operation, the slower the cipher becomes. So the larger the key, supposedly the more secure the cipher, but also the slower it becomes. So for example, AES 128 is the fastest of these ciphers, and AES 256 is the slowest. Now, AES is built as what's called a substitution permutation network. It's not a Feistel network. Remember that in a Feistel network, half the bits were unchanged from round to round. In a substitution permutation network, all the bits are changed in every round, and the network works as follows. So here we have the first round of the substitution permutation network, where the first thing we do is we XOR the current state with a round key, in this case the first round key. Then we go through a substitution layer where blocks of state are replaced with other blocks based on what the substitution table says. And then we go through a permutation layer where bits are permuted and shuffled around. And then we do this again. We XOR with the next round key, we go through a substitution phase, and we permute the bits around. And so on and so on and so forth until we reach the final round where we XOR with the very last round key, and then out comes the output. Now, an important point about this design is that, in fact, because of how it's built, every step in this network needs to be reversible so that the whole thing is reversible. And so the way we would decrypt, essentially, is we would take the output and simply apply each step of the network in reverse order. So we start with the permutation step, and we have to make sure that step is reversible. Then we look at the substitution layer, and we have to make sure this step is reversible. And this is very different from DES. In DES, if you remember, the substitution tables were not reversible at all. In fact, they mapped 6 bits to 4 bits, whereas here, everything has to be reversible, otherwise it would be impossible to decrypt. And of course, the XOR with the round key is reversible as well. Okay, so inversion of a substitution permutation network is simply done by applying all the steps in the reverse order. So now that we understand the generic construction, let's look at the specifics of AES. So AES operates on a 128-bit block, which is 16 bytes. So what we do with AES is we write those 16 bytes as a 4x4 matrix. Each cell in the matrix contains 1 byte. And then we start with the first round. So we XOR with the first round key. And then we apply a certain function that includes substitutions and permutations and other operations on the state. And again, these 3 functions that are applied here have to be invertible so that, in fact, the cipher can be decrypted. And then we XOR with the next round key, and we do that again. Again, we apply the round function and XOR with the round key, and we do that again and again and again. We do it 10 times, although interestingly, in the last round, the mixed column step is actually missing. And then finally, we XOR with the last round key, and out comes the output. Again, at every phase here, we always keep this 4x4 array, and so the output is also 4x4, which is 16 bytes, which is 128 bits. Now, the round keys themselves, of course, come from a 16-byte AES key using key expansion. So the key expansion maps us from a 16 bytes AES key into 11 keys, each one being 16 bytes. So these keys themselves are also a 4x4 array that's XORed into the current state. Okay, so that's the schematic of how AES works, and the only thing that's left to do is specify these 3 functions: byte sub, shift row, and mixed column. And those are fairly easy to explain, so I'm just going to give you the high-level description of what they are, and those interested in the details can look it up online. So the way byte substitution works is literally it's one S box containing 256 bytes, and essentially what it does is it applies the S box to every byte in the current state. So let me explain what I mean by that. So the current state is going to be this 4x4 table. So here we have the 4x4 table, and to each element in this table we apply the S box. So let's call it the A table. And then what we do is essentially for all 4x4 entries, essentially the next step, Aij, becomes the current step evaluated at the lookup table. So we use the current cell as an entry, as an index into the lookup table, and then the value of the lookup table is what's output. Okay, so that's the first step. The next step that happens is a shift row step, which is basically just a permutation. So essentially we kind of do a cyclic shift on each one of the rows. So you can see the second row is cyclically shifted by 1 position, the third row is cyclically shifted by 2 positions, and the third row is cyclically shifted by 3 positions. And the last thing we do is mix columns, where literally we apply a linear transformation to each one of these columns. So there's a certain matrix that multiplies each one of these columns, and it becomes the next column. So this linear transformation is applied independently to each one of the columns. Now I should point out that so far shift rows and mixed columns are very easy to implement in code, and I should say that the byte substitution itself is also easily computable, so that you can actually write code that takes less than 256 bytes to write, and you can kind of shrink the description of AES by literally storing code that computes the table rather than hardwiring the table into your implementation. And in fact, this is kind of a generic fact about AES, that if you kind of allow no pre-computation at all, including computing the S box on the fly, then in fact you get a fairly small implementation of AES, so it could fit on very constrained environments where there isn't enough room to hold complicated code. But of course this would be the slowest implementation because everything is computed now on the fly, and as a result the implementation obviously is going to be slower than if things were pre-computed. And then there's this trade-off. For example, if you have a lot of space and you can support large code, you can actually pre-compute quite a bit of the 3 steps that I just mentioned. In fact, there are multiple options of pre-computations. You can build a table that's only 4 kilobyte big, or you can build a table that's even longer, maybe 24 kilobytes. So basically you'll have these big tables in your implementation, but then your actual performance is going to be really good because all you're doing is just table lookups and XORs. You're not doing any other complicated arithmetic. And as a result, if you can do a lot of pre-computation, these 3 steps here, byte sub, shift rows, and mixed columns, can be converted just into a small number of table lookups and some XORs. All you can do is just compute the S box, so now your implementation would just have 256 bytes hard-coded. The rest would just be code that's actually computing these 3 functions. The performance would be slower than in the previous step, but the code footprint would also be smaller. So, and overall, there's this nice trade-off between code size and performance. So on high-end machines, on high-end servers, where you can afford to have a lot of code, you can pre-compute and store these big tables and get the best performance. Whereas on low-end machines like 8-bit smart cards, or think of like an 8-bit wristwatch, you would actually have a relatively small implementation of AES, but as a result, of course, it won't be so fast. So here's an example that's a little unusual. Suppose you wanted to implement AES in JavaScript, so you can send an AES library to the browser and have the browser actually do AES by itself. So in this case, what you'd like to do is you'd like to both shrink the code size so that on the network there's minimum traffic to send the library over to the browser, but at the same time you'd like the browser performance to be as fast as possible. So this is something that we did a while ago. Essentially the idea is that the code that actually gets sent to the browser doesn't have any pre-computed table, and as a result it's fairly small code, but then the minute it lands on the browser, what the browser will do is it will actually pre-compute all the tables. So in some sense the code goes from this being small and compact, it gets bloated with all these pre-computed tables, but those are stored on the laptop, which presumably has a lot of memory. And then once you have the pre-computed tables, you actually encrypt using them, and that's how you get the best performance. Okay, so if you have to send an implementation of AES over the network, you can kind of get the best of all worlds, where the code over the network is small, but when it reaches the target client, it can kind of inflate itself and then get the best performance as it's doing encryption on the client. Now, AES is such a popular block cipher. Now, essentially, when you build crypto into products, essentially you're supposed to be using AES. And as a result, Intel actually put AES support into the processor itself. So since Westmere, there are special instructions in the Intel processor to help accelerate AES. And so I listed these instructions here. They come in two pairs, AES enc and AES enc last, and then there's AES keygen assist. So let me explain what they do. So AES enc essentially implements one round of AES, namely apply the three functions in the XOR with the round key. And AES enc last basically implements the last round of AES. Remember, the last round didn't have the mixed columns phase. It only had the subs bytes and shift rows. And so that's what AES enc last does. And the way you call these instructions is using 128-bit registers, which correspond to the state of AES. And so you would have one register containing the state and one register containing the current round key. And then when you call AES enc on these two registers, basically they would run one round of AES and place the result inside of this XMM1 state register. And as a result, if you wanted to implement the whole AES, all you would do is you would call AES enc 9 times, and then you would call AES enc last 1 time, and these 10 instructions are basically the entire implementation of AES. That's it. It's that easy to implement AES on this hardware. And they claim because these operations are now done inside the processor, not using external instructions, they're implemented in the processor, they claim that they can get a 14x speed up over, say, an implementation that's running on the same hardware, but implementing AES without these special instructions. So this is quite a significant speed up, and in fact there are now lots of products that make use of these special instructions. And let's just say that this is not specific to Intel. If you're an AMD fan, AMD also implemented exactly kind of similar instructions in their Bulldozer architecture and further in future architectures. Okay, so let's talk about the security of AES. I want to mention just two attacks here. Obviously, AES has been studied quite a bit, but the only two attacks on the full AES are the following two. So first of all, if you wanted to do key recovery, the best attack basically is only 4 times faster than exhaustive search, which means that instead of a 128-bit key, really you should be thinking of AES as a 126-bit key, because exhaustive search really is kind of 4 times faster than it should. Of course, 2 to the 126 is still more time than we have to compute, and this really does not hurt the security of AES. The more significant attack actually is on AES 256. It turns out there's a weakness in the key expansion design of AES, which allows for what's called a related key attack. So what's a related key attack? Essentially, if you give me about 2 to the 100 input-output pairs for AES, but from 4 related keys. So these are keys that are very closely related. Namely, key number 2 is the same as key number 1, except that a few bits of key number 1 have been flipped. Similarly, key number 3 is the same as key number 1, except that a few bits are flipped, and the same for key number 4. These are very closely related keys. If you like, their Hamming distance is very short. But if you do that, then in fact, there is a 2 to the 100 attack. Now you should say, well, 2 to the 100 is still impractical. This is still more time than we can actually run today. But nevertheless, the fact that it's so much better than an exhaustive search attack, is so much better than 2 to the 256, is kind of a limitation of the cipher. But generally, it's not a significant limitation because it requires related keys. And so in practice, of course, you're supposed to be choosing your keys at random so that you have no related keys in your system, and as a result, this attack wouldn't apply. But if you do have related keys, then there's a problem. So this is the end of the segment, and in the next segment, we're going to talk about more provably secure constructions for block ciphers.